Bringing a modern 120 megawatt data center online requires absolute precision control over massive amounts of continuous electrical energy. A professional power system study functions as a cohesive analytical workflow where every calculation output becomes the mandatory input for the next. Inside software like ETAP, this forms a rigid, sequential mathematical chain. This creates a strict vulnerability. A single incorrect assumption entered at the initial modeling stage structurally compromises all downstream results. If initial data is wrong, protective relay coordination fails. Arc flash calculations become unreliable. Harmonic resonance predictions become useless. The software output is entirely dependent on the rigor of the input data. Entering flawed assumptions at the model level guarantees errors during real-world procurement and safety testing. We establish the baseline system by mapping the facility's topology. Power flows from a 150 kilovolt utility grid, steps down to a 20 kilovolt medium voltage switchgear, passes through transformers to low voltage switchboards, UPS units, and final data hall loads. Once mapped, we execute a strict analytical sequence: steady-state load flow, short circuit analysis, protective device coordination, arc flash evaluation, and harmonic studies. Executing this sequence guarantees the electrical network maintains stability, selectivity, and safety across vastly different operating states. To calculate these states, engineers assign per-unit impedance to the model. This is a normalized mathematical baseline that dictates how current flows and how electrical faults behave within the simulation. Assuming incorrect physical data, such as guessing a cable length or misinterpreting a transformer's internal impedance, invalidates the accuracy of the per-unit model. Before we evaluate any catastrophic short circuit, the steady-state thermal constraints and baseline voltages of the system must be proven mathematically absolute. Load flow analysis serves as the mandatory first step. It verifies the steady-state capacity and thermal loading of the equipment under standard conditions. This split screen illustrates how we determine apparent power, measured in kilovolt amperes, and track voltage drop across the system's cables. Cable resistance and reactance cause the 400-volt source to degrade. If the calculation yields an 8.65% drop, the feeder fails design criteria. Pushing that much current through an inadequate path has severe physical consequences, like overloading a 2 megavolt ampere transformer and invalidating all baseline thermal assumptions. Engineers mitigate these load flow failures by specifying larger cross-sectional cables or installing parallel cable runs to lower the total impedance. If the electrical system fails mathematically in normal steady-state operation, any downstream fault or safety analysis is inherently invalid. With the steady state secured, we transition to short-circuit analysis. This determines the absolute maximum and minimum available fault current at every single bus in the facility. We track a fault originating from the primary utility source. The utility's short-circuit capacity translates to 6.21 kiloamperes hitting the medium voltage switchgear. Downstream, system impedance acts as friction. A theoretical 48.1 kiloampere transformer fault drops to 39 kiloamperes at the main switchboard. We must study two precise extremes: the maximum possible fault current and the minimum possible fault current. Maximum fault currents define the equipment withstand ratings. We calculate this ceiling to ensure the physical circuit breakers do not explode under the mechanical stress of a dead short. Minimum fault currents verify that protective devices will actually detect a weak fault and operate effectively before the cables reach their thermal damage limits. By establishing these absolute upper and lower boundaries, short-circuit analysis provides the exact operating parameters needed for protection coordination. A common misconception in the industry is the assumption that the highest available fault current automatically generates the highest arc flash hazard. Arc flash incident energy is measured in calories per square centimeter. That energy output is directly proportionally tied to the clearing time of the protective device. This creates a paradox. A lower fault current might fail to trigger a breaker's rapid instantaneous trip mechanism, forcing the breaker to rely on its slow, long-time delay sequence. This TCC curve and data table show how this paradox plays out for a downstream PDU tap-off. The table records a fault clearing time of 588.54 cycles. We divide those cycles by 50 Hz, giving an actual fault duration of 11.77 seconds. Cycles are purely a measure of duration. They measure time, not thermal energy, and the two values must never be confused. By allowing an electrical arc to burn for almost 12 full seconds, the resulting incident energy spikes to 31.5 calories per square centimeter. An energy output of 31.5 is a severe level E hazard. Approaching that equipment requires specialized personal protective equipment. Because incident energy is roughly proportional to the duration of the arc, controlling time controls the hazard. If we adjust the relay settings to force a 0.10-second clearing time, that hazard drops from 31.5 back down to safe, manageable levels. Optimal protection coordination requires a calculated balance. The engineer must maintain selectivity to keep the critical IT loads online while clearing faults fast enough to prevent lethal incident energy. Modern data centers are dominated by nonlinear loads, primarily the uninterruptible power supply rectifiers and variable frequency drives. Unlike standard equipment, these nonlinear power supplies pull current in abrupt, irregular pulses. This generates significant total demand distortion, or TDD, within the current waveform. When that distorted current flows through the physical impedance of the facility, it forces voltage distortion, total harmonic distortion, across the entire electrical bus. This harmonic analysis executive summary highlights the compliance goal for a modern facility. The total harmonic distortion at the main switchboard panels must remain under 3%. But staying under 3% requires running frequency scans across the network. These scans analyze the system from the fundamental frequency up into the high harmonics, searching for hidden resonance peaks. If a resonance peak aligns tightly with a dominant harmonic order, like the 5th or 7th harmonic, the engineer must model active harmonic filters or detuned capacitor banks to mitigate the risk. Harmonic compliance directly impacts hardware longevity. Unmitigated harmonics cause severe transformer heating and neutral current overloads, which destabilize the thermal baselines established in the load flow calculation. The single most complex variable in modern data center engineering is the sudden transition to emergency backup power during a grid failure. Disconnecting from the utility grid to island on generators alters the system's fault profile and source impedance. Generator fault current behaves differently from utility power. It is limited by the alternator's specific reactance values and decays rapidly over time. Protective devices calibrated for a strong utility grid often fail to trip under the weaker, decaying fault current provided by a generator. Because the source impedance variables change in generator mode, all short circuit limits, relay coordination curves, and arc flash hazard labels must be recalculated. Furthermore, that higher source impedance increases the facility's harmonic distortion profile, requiring the power quality scans to be run a second time. The engineering process follows a continuous quality loop of validation and recalculation. A professional data center power study remains a dynamic mathematical verification of the facility's physical reality, guaranteeing survival across every conceivable operating state.